Okay. I will begin. Heavenly Father, we thank you for the weekend and for the nice weather. Just pray to be with us today. Help us to understand the material we go over, and just pray to bless this class, Lord. Help us to glorify you in what we do, Lord. In your name I pray. Amen. Okay, so what was your question about, actually?
I was just asking if you could show part 10 or 10 part A, because I
10 part A
just couldn't figure it out.
on the quiz. Let's see here. So part A, we're given the total energy of the particle is 3 joules, and your initial position is at 21, and you're supposed to give an approximate possible range of motion, right? So I can actually kind of do this one. This is my best attempt. So it's something like this, right? And so here is 20, right? This is position. This is potential energy, right? And you're told that your total energy is 3 joules. Now, this is about 2, this is about 3, this is in joules, this is in meters, right? So I tell you that your total energy is 3, right? So this is the total energy level right here, right? Now, this is forbidden because that would mean that, the total energy is 1/2 mv squared plus u, right? So given that that's positive, you can't have a total energy which is less than the potential energy that would correspond to this term being negative, which we can't do, right? So this is actually forbidden. Likewise, this is forbidden. So possible motions are really in here and in here in this picture. So if you start at 21, which would be something like here in the picture, I think, right? You're either going this way or you're going that way. But anyway, what happens is you either do this, or anyway, your motion is always basically stuck between here and here. In other words, your motion's bounded between these two x values, let's say x1 and x2. So x1 is approximately, x2 is approximately, looking at the graph that I gave you guys, I should make it bigger. Just staring at it here for a second. 16, something like that. This is very crude. And 3, if I look at the graph, maybe 25-ish. Something like that, maybe 24. In that ballpark. The point is, I can't get over the potential well. I don't have enough energy. I'm definitely stuck in here, back and forth motion. So the motion is bounded, and it's bounded between approximately like 16 and 24 or something like that. Yeah. And then part B is like what I did in class, but. This is actually a recycled physics problem. I gave this in Physics 231 a couple of years ago. But I think maybe 30% of the students got it. I don't know. It's just, maybe more got it. I don't know. I'm always, this is a very random question. Like when I ask a given class of physics this, it's either like 80% of them get it or like 20% of them get it. It's the weirdest thing. I do pretty much the same examples every time, but I don't know. Maybe it's the homework I assign. I sometimes naively assume that students study what I do in lecture, which may be wrong. I don't know. But I'm not talking about you guys. But all right, let me stop. All right, so getting back to Laplace transforms. So I mentioned this idea of exponential order alpha last time, but I haven't really exposited much on that. So let me just take a minute to do that. So definition, all right, f a function from, let's say, 0 to infinity to the reals has exponential order alpha if there exists some m which is greater than 0, greater than or equal to 0, and alpha such that the magnitude of f of t is less than or equal to m e to the alpha t. I feel like I have this moment of, is alpha supposed to, am I missing a minus in here or something? Just give me a second, guys. Come on. So you guys have read the chapter on Laplace Transforms. Is it in there? No? No one knows? Well, it is a PDF, so I can search exponential order and see where it takes me. So this is actually theorem 6.2.10 I'm working on at the moment. And the definition I just wrote down is definition 6.29 on page 168 of my notes. And no, there's no sign. It's fine. Oh, but this isn't, this is for, well, there's also a t, which is greater than 0, and this is, or equal to 0. This is for each t which is beyond big T, all right? So the idea here basically is that the function is such that if you go beyond some point, you can bound it by an exponential times a constant. So it doesn't grow faster than an exponential eventually. Eventually. You can have faster than exponential growth for small times, right? But at some point, there's an exponential that gets beyond it, right? And so if you look at the Laplace transform of, so suppose f is such a function, take the Laplace transform of f, right? Well, that's the integral from 0 to infinity of f of t e to the minus st dt. And, you know, just basic integration stuff, that's going to be less than or equal to the integral from 0 to infinity of the absolute value of f of t e to the minus st dt, right? The integral, youngins, campers, I think. All right. My kids are all in camp now. Well, not all of them, but my boys. See, Daniel's gone to some video game camp. And they're programming a video game. It's not as bad as it sounds at first. And then worse, much, much worse, this concerns me actually, is my other son, Isaac's in a soccer camp. I have misgivings about this. This is my wife's idea. I wouldn't have been for this. Or football for the international audience out there. So many of them watching. Let's hear it. Sorry. I'm only partly kidding, actually. So most of the comments I get, people who really enjoy what I'm doing on this channel, a lot of times are international students who have the misfortune of having a very bad teacher somewhere. I mean, they exist. But, I mean, I'm better than that teacher, right? So there you go. But, yeah. Sorry. Anyway, so this is, I'm just saying the integral of the absolute value of function is larger than the function, right? I mean, this is not shocking. And then you can break this up into the integral from 0 to t of the absolute value of f of t e to the minus st dt, plus the integral from t to infinity of, let's say, and then here, let me just do a little bit less writing here. So this is just the first piece. And then the second piece, I'm going to replace with something bigger. In particular, I'm going to replace f of t. I'm going to replace it with m e to the alpha t times e to the minus st dt, right? So I can do that by the given assumption about exponential order alpha. Now, here's the deal. I'll just get to it. Just get to it. This is just a number, right? I mean, assuming that f is a function, I mean, we could just tack this on. Assuming that f is a function such that the integral from 0 to that big T is finite, that piece is controlled, right? It's not going to blow up or anything. And how about this piece over here? Well, this is basically m. And then this algebra tells me what? This is e to the t times what? Minus t times s minus alpha, if you like. Right? So that integrates to m over minus s minus alpha. I don't know why I'm putting the minus like that, but whatever, I did it. It's too late. And then e to the minus t times s minus alpha, right? Evaluated from 0 to infinity. But if we have what? If we have, so for, if s is greater than alpha, what do we get? If s is greater than alpha, s minus alpha is positive, right? So minus t times s minus alpha is negative. I mean, so if you plug infinity into t, you get e to the minus infinity, which is 0. And on the flip side, you get e to the 0, which is 1, right? So again, this finite number, right? Provided that s is greater than alpha. And so there's the theorem. So the theorem is, I'll write it here, theorem. The Laplace transform of f of t of s exists for s greater than alpha. If we have a function with exponential order alpha, then we can be assured that its Laplace transform exists, provided that we have s greater than alpha. Now you start thinking about polynomials. Like one of the things you should learn in Calculus 1 is that if you have a battle between a polynomial and an exponential, who should you pick? I mean, who's going to win? Exponential, right? Yeah, exponential's going to win. Eventually. Maybe not at the start, right? But eventually the exponential wins. So polynomials are tamed by exponentials. Sines and cosines certainly have exponential order alpha, right? If you take an exponential times sine or cosine, again, you can prove it has exponential order alpha. All of our favorite solutions to constant coefficient ordinary differential equations, exponential order alpha. And we saw that last time because we calculated the Laplace transforms and they worked out, right? What were those? Let's remind ourselves. All right, 5 more minutes. It's perilous for me to be my own cameraman, you know. Ooh, look, it's not on the level. Some real-time leveling. There we go. So what Laplace transforms did we learn last time, and what theorems do we know about Laplace transform technique? Let me rattle them off. Here's the basic ones. Laplace transform of, actually, I'm going to get sick of writing L. Let me make a table form for our results. So we have, let's say, f of t here. We have f of s over here, which is, of course, the Laplace transform of f of t of s. And what we have, the first one I did was 1. It had a Laplace transform of 1 over s, right? Next, I did e to the at, and we learned that the Laplace transform of that was 1 over s minus a, right? Then I said, basically a could be complex. I replaced a with lambda, and we derived that if we have e to the alpha t cosine beta t, then we get s minus alpha over s minus alpha squared plus beta squared. And the other one, e to the alpha t sine beta t, was just beta over s minus alpha squared plus beta squared. The other one we did at the very end of class, I believe, was we figured out the Laplace transform of t to the n. It was n factorial over s to the n plus 1, right? And let's see here, we had maybe 3 important theorems last time, I think. What were they? First of all, the Laplace transform of e to the at times f of t was what? The so-called Shift Theorem says to take the Laplace transform of the exponential times a function, we just take the Laplace transform of the function itself and shift s to s minus a, so-called Shift Theorem, right? The other, I think the notation I used last time probably was big F of s minus a. You can see this theorem in action if you look at row 1 to row 2 here, right? The other theorem we learned, which is probably maybe the most important theorem, is that the Laplace transform of the derivative, let's say y prime, is equal to s times the Laplace transform of y minus y of 0, right? That assumes that y has exponential order alpha. And then, of course, the Laplace transform of y prime prime is s squared times big Y minus s times y prime of 0 minus y of 0. Am I right?
It's minus y prime 0. So s y 0 minus y.
Aha, so I have them, yep. That's the main place people mess it up. Now, you guys have no excuse to do that because you get a formula sheet, right? So you should get that out of your system. I personally can't get it out of mine. This is a canonical mistake I make. Anyway, it's a standard mistake. And we did for higher derivatives, but that will suffice for the moment. And then we also proved that the Laplace transform, no, excuse me, the derivative, how was it good? The derivative of the Laplace transform, I'm not liking my notation. I'm going to use big F for the Laplace transform here because it's more fun. So the Laplace good gracious, DDS of F, right, was equal to minus 1 times the Laplace transform of t times F. Fine. It's bothering me. I'll use this stupid other notation everywhere. I'll get it out of my system here in just a second, guys. There. I'm just saying the derivative of a Laplace transform is minus the Laplace transform of t times that function. And generally, if we have the nth derivative of the Laplace transform with respect to the transform variable s, we get minus 1 to the n times the Laplace transform of t to the n times f of t of s. As far as I can remember, those are all the theorems that we worked out last time. There's also another more important, actually this is I've buried the lead. The lead theorem really is this, that the Laplace transform of, c1y1 plus c2y2 is what? c1 Laplace transform of y1 plus c2 the Laplace transform of y2. In other words, the Laplace transform is linear. You can break it up across addition, and you can pull constants out, right? So this is nice. What was our strategy for solving a differential equation? and not just an equation, but an initial value problem. So we've got something like, so step 1, we take the Laplace transform, it changes y prime, y prime prime, y prime, and y to big Y, and swaps t for s, right? So you take the Laplace transform, taking the Laplace transform of the differential equation itself swaps out our dependent variable little y for dependent variable big Y, which is a function of the the s. And then step 2 was to solve for big Y, right? Equal stuff. And then step 3 was to say little y is equal to the inverse Laplace transform of stuff, right? But to actually carry out step 3, we need the technique of partial fractions and a few other tools. All right? To do this requires some algebra. Let's see here. Eeny, meeny, miny, mo, catch a tiger by its toe. If it hollers, let him go. Eeny, meeny, miny. Oh, sorry, Isaac. You're like, there's more to it. No, I don't know the rest of it. Okay, so let's get to work on how we calculate the inverse Laplace transform of things, all right? So just to be clear, L inverse of f is equal to little f means that the Laplace transform of big F is equal to, of little f is equal to big F. Right. Fundamental theorem of inverse Laplace transforms, it's linear. All right, so I can also break up across addition, pull scalars out. All right. The inverse of a linear operation is also linear. It's a theorem. So I think the best thing for me to do at this point is just try to start showing you a series of examples. Start out small here. So what would be the inverse Laplace transform of, let's say, 3 plus s over s minus 7? So here we have an example of what's called an improper rational function in S, right? I have a linear upstairs, I've got a linear downstairs. So we could do synthetic or long division, right? We could use my trick. I'm going to do that. This is really the inverse Laplace transform of S minus 7. To get a 3 back, I have to do what? To be fair. Algebra demands I put what else in the numerator? Yeah, that has to be 3 plus s. It's true. I put s minus 7. I started with 3 plus s. What else do I need for the numerators to be equal before and after the equality? Yeah, plus 10. Now, the reason I did that, I think, is fairly obvious, right? I mean, now we can use algebra, and that's really the inverse Laplace transform of 1 plus 10 over s minus 7, right? And so what's that? That's going to give me 1 over s, yeah, plus 10 times e to the 7t. I'm sorry, I can't do math. Oh, no. No, 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 no. What's the inverse Laplace transform of 1? In other words, is there anything here that's just the number 1? It's not the case, right? I'll tell you. This is really from about an hour later in the lectures, maybe an hour and a half. Hopefully we'll get to it toward the end of today. But like if you take the Dirac delta function of t, it's the Laplace transform as 1. The Dirac delta function is not actually a function. This is a very bad example on my part. I'm sorry, guys. I mean, I should say it's just like I planned. I was giving you a forewarning of things to come. But the larger point here, though, is it's not hard to come up with things that the inverse Laplace transform may take you to a place you don't want to go. And this is actually such a, oh, not 1, but delta of t. Yeah. Yeah. Ouch. To draw a graph of that thing, I just did. I mean, this is the graph of the delta function. It's basically 0 if t is not equal to 0, and it's infinity if t is equal to 0. And it's infinity in such a way that the area under the graph is 1. Now you're like, I'm not the best Calculus 1 student, but I'm pretty sure you can't do that with a function. Very good. That's right. You can't have finite area under 1 point in a function. It's not technically a function. It's something called a distribution, the mathematics of which we're not going to do properly in here. But you're like, well, then why are you doing it? Well, engineers and physicists use Dirac delta functions all over the place. They're the right mathematical tool to do things like model, say, a point charges. Like, what's a point charge? Think about this. If I have the line, right? Like, here's the real line. I put a charge q right here. If rho, well, I guess I need some other letter. Say lambda is equal to dq dx. You know, it's the charge per unit length. What's the right formula for having a point charge located, say, at x naught? Well, let's put it x equal to 0 just to keep things simple. Well, the right formula for that is actually q Dirac delta function of x. The way that works is if you integrate the density over a line segment which includes the origin, you get q. On the other hand, if your domain of consideration doesn't include the origin, you don't get q. That's exactly what we mean by a point charge. The charge is localized at the origin, and all of it's there. So we need this thing called the Dirac delta function to describe things like localization of charge and other things. But anyway, I'm sorry, I got a little bit ahead of the story, and so I will do better. My next example will not take us 2 hours into the future of our work. Okay, sorry about that. My bad. Let's try this again. Example 2. How about the inverse Laplace transform of s plus 6 over s squared minus 3s plus 2? So here we need something called partial fractions. I'll show you how it goes. So this factors is what? This is s minus 1 times s minus 2, right? The denominator is s minus 1 times s minus 2. So there's a partial fractions decomposition of this, and in particular as follows. I can write s plus 6 over s squared minus 3s plus 2 as some particular combination, let's say a over s minus 1 plus b over s minus 2. All right? This is that partial fractions algebra you did in Calculus 2. Remember? To integrate rational functions, we had to do this. And so you multiply both sides by the denominator. And that gives us s plus 6 is a times s minus 2 plus b times s minus 1. And let's see here. If you put in s equals to 2, what do we get? If you put in s equals to 1, what do we get? I put s equals 2. In the left-hand side, what's 2 plus 6? It's 8, right? So we get 8. On the right-hand side, put in 2. It kills the a term, and it leaves b as b. Okay, well, yeah. So apparently b is 8. Okay, great. Well, this equation was kind of pretty simple to solve. S equals to 1, on the other hand, it gives me what? It gives me 7 equals to, what is it? Negative a, right? So a is apparently minus 7. So we put that up into here, and we have as the inverse Laplace transform of the thing originally, right? The thing originally I'm stuck with, right? If you go back to our table of known Laplace transforms, it's not there, right? But after I do the math, I've got minus 1 over s minus 1, right? Plus 8 over s minus 2. We're good to go. We can use linearity of the inverse transform, and the answer is apparent, right? This gives me what? Minus?
Minus 7.
Oh, no, you're right. Minus 7. Thank you. Just making sure you guys are paying attention. Of course, I didn't do it on purpose. Thank you. Yes, minus 7. Sorry. And so what we got? Minus 7 e to the what? E to the t plus 8. What is it? E to the 2t. There you go. Our first reasonable inverse Laplace transform. Is it better? I mean, I did one at the end of last class that I used kind of similar algebra than I did in example 1 to do that example as well, right? I mean, all right, let's go on. No substitute for a bunch of examples. So let's just keep, I'm gonna example you to death here, if you don't mind. Here's another one, example 3. And I'll put it over here a little bit. Example 3. Let's calculate the inverse Laplace transform of 3s plus 7 divided by s squared plus 8s plus 25. So the first order of business, anytime we've got a linear over a quadratic, we have to understand what kind of denominator we're dealing with. All right? If it's a distinct linear, if it factors over the reals, then the technique we used in example 2 will work. We can do partial fractions like we just did. This is not that, though, right? This, if we complete the square in the denominator, it reveals its true nature here, which is what? This is really s plus 4 quantity squared, right? Plus what? 9, right? I'll write it as 3 squared just to emphasize what's going on here. Partial fractions doesn't help you here. What you got to do here is just plain old arithmetic. So this means we're going to get what? Like, so you got to think a little bit. And if you think, you should see that we're going to get things like e to the minus 4t, cosine 3t, or e to the minus 4t, sine 3t type terms, right? Again, I'm looking at this. I'm thinking going backwards, right? To go from here to here is the inverse Laplace transform, right? To go from this to there is the Laplace transform. So we're trying to go the other direction. So in order to go the other direction, to bridge the gap, we got to find these things, right? The reason I did partial fractions in example 2 was because when I just look at the initial expression, I don't know how to take the inverse transform, but after I do the algebra, I can. Again, I don't know. So what I got to do, I'll deal with kind of the nastiest thing, which is this 3s. So the way I do this, and I mean, there'd probably different people have different approaches, but I'm going to say that's 3 times s plus 4, right? I need that, right? That's going to lead to a cosine term. Once I do that, what's that do? Effectively, that's like what? Adding 12, right? What did I have to start with? 7. So I just made up 5 that wasn't there. So to be fair, I have to subtract 5. Now, so almost done, right? So I don't always put down this step, but I will at this point because we're starting. So this inverse Laplace transform of s plus 4 over s plus 4 squared plus 9. I'm using linearity of the inverse transform now. And then I have minus 5 over 3 inverse Laplace transform of 3 over s plus 4 squared plus, I'll write it as 3 squared again to emphasize where the 3 is coming from, right? The reason I put a 3 there is I need it for the inverse transform, right? There's a beta upstairs for the sine transform. I need that 3 to be there, otherwise I can't go backwards, right? These are sort of like a network of tunnels or something, you know, between the S domain and the T domain, and you have to like line up to the tunnel entrance just right, otherwise you can't go through it. So like that 3 there is necessary to go, you know, sort of sink into that formula, and I need the S plus 4 there to sync up with this formula. Yeah.
So just by looking at the denominator, you don't know for sure if it's a cosine or sine term for the Laplace transform. You have to look at the numerator.
Yeah, for a given denominator, I can get sines or cosines. Yeah. There's a very similar calculation you could do in terms of coshs and sinh. Like you could always do this if you're willing to either go cosh sinh or cosine sine. But I think the partial fractions technique is faster for actual problems. So I do what I did. So this then is what we got. We got 3 e to the minus 4t cosine 3t minus 5/3 e to the minus 4t sine 3t. Yep. Now the other possibility for a linear over a quadratic, we saw the example at the end of last class where we had a repeated root, right? That was the other thing that could have happened. Here, I'll do another one of those right quick. Example 4. Before I do, though, any questions? Try to keep this one relatively simple. Inverse Laplace transform of s over s squared plus 6s plus 9. That's what? Well, this time the denominator is That's s plus 3 quantity squared, right? Again, if you look over here, you notice that we don't have anything like that, right? But what we do have, I guess one that might be good to add to this, if I was going to get rid of my delta, put in something more useful, t e to the at Laplace transforms to 1 over s minus a squared. That's the shift theorem if you apply it to this with n equals to 1. Oops. So anyway, but you notice that this isn't that, right? I mean, it's not the right, doesn't match. So what am I going to do? Have you discovered my ninja way yet? Sorry, I've been watching a lot of Naruto. I usually add 0 or multiply by 1. You notice I multiply by 1 here, 3 over 3. I added 0 up here somehow. But just add and subtract 3. I mean, that will do the trick. If we do that, then you can see that this is the inverse Laplace transform of 1 over s plus 3 minus 3 over s plus 3 squared. All right? And that is going to give me e to the minus 3t minus 3t e to the minus 3t. And there you go. So if we're dealing with a linear expression in s divided by a quadratic expression in s, these are the things that can happen. Distinct exponentials, exponentials times sines and cosines, or mixture of exponentials and t times the exponential. Of course, if you just have like s squared plus something, then it's going to give you pure sines and cosines, right? We'll see that in the next example. Any questions? Yeah? It's s plus 3 squared, so that's like this. The inverse, put a equals to minus 3. It's the inverse transform of that. Yeah. Oh. My battery, my battery. No. Come on. Come on. Forgot to plug in my computer. And I was outside working on my back table before I got here because the weather is amazing right now. It's nice. Although, not as nice when I went to the pool last night. Like, I'm not like the kids. I'm not like swimming around. I'm just sitting there watching them, you know. I'm like, it's cold. It's cold. It's cold. Here. All right. Next example then. Let's see here. We could suppose f of s is equal to, let's say, s squared plus 4s plus 2 divided by, don't look at me, s cubed minus 3s squared plus s minus 3. Now this is a cubic, right? Oh, I guess we don't need the how to solve it just yet. We'll get back to those before today's done, don't worry. But okay, so I guess the issue is we got to factor this denominator. Can you see anything? What's that?
S minus 3.
Oh, there's an s minus. You can see you see factoring by grouping, right? Yeah. So this is really s squared times s minus 3 plus 1 times s minus 3, right? So in fact, this mysterious f of s, you undid my multiplication, very good. S squared plus 4s plus 2 over s squared plus 1 times s minus 3, right? Now this time partial fractions is a little bit more interesting. Generically speaking, you should remember how it goes from calculus 2. If we have a, say, third order thing in the denominator, there should be 3 undetermined, well, to be determined coefficients in the partial fractal decomposition. So I should expect an ABC. In this case, I would have, oops, a plus bs over s squared plus 1 plus c over s minus 3. Right? Now, let's see, that will give me s squared plus 4s plus 2 equals to a plus bs times s minus 3 plus c times s squared plus 1, right? There are various ways to do the algebra here. I'm going to go ahead and sort of multiply this out. This is giving me s squared times what? Of course, I got the c over there, but I've also got b plus c, yeah? What are the coefficients of s? For s, I've got a minus 3b, and I've also got plus a, yeah? What are the constant terms here? Yeah, c minus 3a, right? So here we have a quadratic in s on both sides, and we can equate the coefficients. So equating coefficients, so I've got my s squared, I've got my s, and I've got my constant. So s squared gives me 1 equal to b plus c. My s gives me 4 is a minus 3b. And my constant terms are 2 equal to c minus 3a. Now, is there another I mean, you don't have to, you can use our previous method to get another very easy equation which will make life easier. What's immediately obvious if you go back to star? Set s equal to what? S equal to 3 gives us what? It gives us 9 plus 12 plus 2 equals to what? 0 and 10c. See, that's pretty nice what I wrote in the blue, because that gives us the solution for c without really doing much algebra at all. So c is equal to, what is it? C is equal to 23 over 10. That's nice, because now I can use that with my other equations to figure out what b and a are, right? Of course, what I wrote in blue, you don't have to do. You could solve 3 equations and 3 unknowns and get to the same thing. a question of attack, all right? Okay, so I'm going to have B is 1 minus C, which is 10 minus 23 over 10, aka minus 13/10 equals to B. And let's see here, I think equation for S is nice for A. A is equal to 4 plus 3B, which is equal to 40 plus 3 times 23 over 10, which of course is 69 plus 40, 109 over 10, I think. Don't be afraid to check your work here. You know, all you got to do is put, you know, s squared plus 4s plus 2 divided by that stuff, and like the word partial fractions into Wolfram alpha, it'll spit out what the answer should be, right?
For A, it's minus 3B.
What have I done?
I think we wrote it.
Oh,
Wait, oh yeah, yeah.
it's B. Your point is well taken, though. It's B, not C, right? I was putting C in here. It's B that I'm supposed to be plugging in, right? So that's supposed to be minus 13. I did see that. That did seem awful big. Thank you. Oh, that's neat. So that's actually minus 30. So it's just 1/10, yeah? Right? 1/10? Because I get 40 minus 39, which is 1. Do we agree now? Okay. Okay, so let me put the fruits of our labor up here. We have, oh, fine, let me behave and write it over somewhere else. It's confusing to the reader, right? If I go back to an earlier point in time and time travel the answer back to the start of my solution, right? That's kind of a bad habit. We should all write solutions with pens that have like an ink which changes with time, right? So as the color changes, you could tell at what point in time you're in the solution. But then that would make making corrections to your solution really complicated, right? You'd have to have like a reverse time pen or something, or like a, I don't know. I'm sorry. Let me shut up. F of s is what? F of s equal to, for this marker, what we got? 1/10 was my B, minus 13 over 10 times s, all divided by s squared plus 1. Right. And then, what was C? Plus 23 over 10 times 1 over s minus 3. All right, now we're good to go, because at this point, it's easy to take the inverse Laplace transform, right? So take the inverse Laplace transform, and what do we get? We get f of t 1/10 sine t minus 13/10 cosine t plus 23 over 10 e to the 3t. Hooray. There we go. I'm allowed to do a fun example, right? Right? Yes. Any questions for John here? Example 6, how about this? How would you calculate the inverse Laplace transform of, like, I don't know, how about 1 over s to the 4th minus 81? So here, what you got to notice is that s to the 4th minus 81 is actually s squared minus 9 times s squared plus 9, right? And let's see here. So we expect then that 1 over s to the 4th minus 81 is going to be something like as plus b over s squared minus 9 plus cs plus d over s squared plus 9. I'm breaking from example 2. I have the intention of using Cauchy cinch for this example. So you can, this right here, I mean, the other way to do this, of course, would be something like a over s minus 3 plus b over s plus 3, right? But I'm going to use Cauchy cinch for a change. Now, what are a, b, c, and d? I mean, I think you can see that this is actually 1/2 1 over s squared minus 9 minus 1 over s squared plus 9. Am I right? The s squareds cancel. Ooh, I'd actually get 18 upstairs from that. So I think I better have 1/18. Guys, just truth in advertising here. I should let you know that this right here, I guessed. All right? But guess and check is also an allowed method, Once you have this, how do you get back to there? You make a common denominator, right? So multiply this by s squared plus 9 over s squared plus 9. That gives me s squared plus 9 up here. Get this back to the denominator, I have to multiply this by s squared minus 9 over s squared minus 9. That puts an s squared minus 9 up here. So the s squareds cancel, and I get 9 minus a minus 9, otherwise known as 18. Divide by 18 gets me back to 1. Or you could go through the algebra like we did. But anyway, with that done, the inverse Laplace transform of 1 over s to the 4th minus 81 of t is going to be 1/18. This guy is actually 1/3 sinh of 3t. And this guy is minus 1/3 sine of 3t. Or if you like, this is 1 over 54 sinh 3t minus the sine of 3t. Now, as I have told you guys, or started telling you guys, you can do things without the Cauchy. Come on. Man, stupid computer. Charge. Like I plug it in, right? But it's not really plugged in. As I've mentioned, my son Matthew dropped the computer about a half year ago, and ever since then I've been playing this Is the Computer Really Charging game, which is very sad, because it's otherwise a very nice computer. Very sad. Now, you can do this with just exponentials, right? If you did it with exponentials, the partial fractions decomposition would have taken this and replaced it with like a over s plus 3 plus b over s minus 3. Different say a tilde, b tilde. I mean, that would have been that. And that would have led you to e to the minus 3t and e to the 3t type